Right, so I'm here to talk about live coding and JavaScript. So what do we mean by live coding? It's certainly not jumping about pretending you're a rock star. It's what we're interested in, what we mean by live coding is when we write code and we can load it into a program without stopping the program from running. We want to be able to keep that program running with kind of minimal loss of state. And as a corollary of this, we should see no perceivable change in the behavior of the program, except, of course, for any change we meant to effect upon that program by our change. But that's really what I mean by live coding. And there's a bunch of different things out there that for this, for different purposes. So we've got things like, that's the screenshot of an overtone session. I don't know if anyone's familiar with that. It's a kind of closure music, live music, generative environment type thing for you write code and you make squeals and bleeps come out the speakers. So there's a bunch of things like that for making live, interactive video, interactive audio. And then we can go into kind of maybe node-based systems, like Quartz Composer, V4, all these things. So the great thing about these things is they provide us it's not maybe programming in the traditional sense, but it allows us to take a bunch of primitive operations and we can kind of stitch them all together and create something that's greater than the sum of its parts. And we can play about with techniques that might have been somewhat laborious to construct if we were doing it in a more standard programming language. Like if you were to try and set up a network like that in a text-based environment, you'd be setting up buffers, you'd be setting up a graph of objects, and you'd be telling them how to route to each other, whereas this is just drag and drop. So that's quite cool. And moving maybe more towards the academic side of the spectrum, we've got things that are called micro-worlds. So this is like maybe Logo, Boxer. Has anyone heard of Boxer? So a Boxer was a kind of evolution of Logo. The idea behind it was there'd be all these nested boxes, but nested boxes would represent some sort of lexical scope. And so if you had a box with a variable name inside it, then you could put a box inside that could reference back to the name. And what they found was that beginners were able to actually create quite sophisticated programs just by the structure that was suggested by the geometry of what they were manipulating. And then we move right to the other end of the spectrum. We've got the academic end. We've got stuff like Smalltalk and Self, kind of typified by what was called the morphic interface. And the thing about the morphic interface was that every sort of object within the system had a graphical representation, and you could modify absolutely everything, right down to the point where even frames on the call stack were objects. So you could manipulate absolutely everything. At runtime, you could drag functions into different objects, you could clone objects, and everything you did had an immediate effect on the screen. And this was born in Self, but that was later co-opted by Squeak Smalltalk as well. So that's an overview of a bunch of different live coding environments that are out there. But why would we want to do this? Why not? The reasons to live code. Is anyone familiar with Brett Victor's videos? Yeah, I've seen those. He's done some amazing stuff where we can tighten the feedback loop. We can tweak programs in real time. We can sculpt things. We can let things evolve rather than planning out this big program and writing it in text and then running it and seeing what happens and then repeating and repeating. We just start with what feels right, and then you can change things and manipulate them, gradually working towards your goal, whether that's a tortoise coming out of a car or whatever. It lets you experiment things that you normally wouldn't try. So, hooking up maybe a REST server to an audio sequencer. If you've got an environment that gives you a bunch of primitives and a simple way to connect these things in ways that normally probably wouldn't occur to you, you can get some crazy results. You can be creative because your mind's freed of the burden of working out how these things fit together, and instead you can just get on with using the bits that are laid out for you. And the final reason to do this, it's just fun. It's a fun thing to do, turning car into a tortoise. Why do it in JavaScript? Well, firstly, it's a flexible language. All of our things are first class. We've got first class functions. We've got first class objects. It's prototypal. In live coding, you're very often you don't work with the class-based paradigm. You're very often just creating a one-off thing and sculpting it and changing it, then maybe cloning it and making a wee tweak. JavaScript's great for this. We've got an amazing ecosystem in JavaScript. We've got the browser, which is great for prototyping user interfaces. Great for, we can capture video. We can do 3D. We can, you can be really explorative with a minimal amount of code. And on the back end, we've got Node.js, which has got a phenomenal ecosystem of code for serious uses, for experimental uses. And all these things can be stitched together to experiment. And then putting the two together. Is anyone familiar with the Node WebKit project? So a few of you. So the Node WebKit project is really just what it says. It's Node.js and WebKit stitched together. So you open up a browser window, but you've got access to all of Node.js underneath. So you can create a web server in your browser. You can access the file system properly from your browser. You can open sockets from your browser, and then all this can manipulate the DOM. You can do all this stuff with practically, very, very little code. JavaScript's single-threaded. Single-threaded languages are great for implementing kind of live coding environments, because you don't have to worry about what your other library that you're using is doing. You can, if you need to hot patch code, you can just load it in, and that goes hand in hand with the event loop, because the event loop gives you JavaScript's one of the few languages that is based solely on an event loop, and this gives you a natural synchronization point. So you can, if you've got changes that you need to load into your code at runtime, you can do them safe in the knowledge that there's nothing else on the stack that you're at risk of destroying. Although interestingly, Olaf Johansson, he's done some great research work with JavaScript and a compiler that can actually manipulate the stack at runtime, and it will do the analysis and work out what variables need to be restored and what kind of transformations are possible and what aren't. So that's a great paper to read if you're interested. So what we find is, very often if we set out to create a general tool to allow us to do anything, they become very complicated. They need to account for every possible use case of every possible user, and that means the end result is something that's optimal for none of them. You also find that the general tools, they're kind of black boxes. They might make unacceptable performance trade-offs that you don't know about. Like if anyone's tried to do anything kind of that pushes the browser to the limits, you very often see artifacts that you wouldn't if you were just programming directly at something lower level. And that's as a result of the fact that we're dealing with a general purpose tool and we're trying to use it for a very specific purpose. So instead of this, I'm interested more in the concept of domain-specific live coding, which is where we evolve a kind of environment along with our application. At every step of the way as we're developing our application, we work out we say to ourselves, what's going to change what do we need to be able to reload at runtime in our program? What do we need to be able to, what state are we happy to lose? What can we absolutely not lose? Is it safe to take snapshots, or can we just take deltas? And as you develop, you work out the answers to these questions, and you evolve with your application an environment that allows you to tweak it as it runs. So I'm going to give you a quick demo of a wee game engine that I've been working on. It's somewhere in here, I think. So this is a very simple little game here, Space Invaders. And what we can do here is we can load up the code of any system, and we can modify this at runtime. And if I click update, you'll see that we get the notification that it's compiled the new code, but absolutely nothing changed on the screen, because it knows how to take the state that's in the game at the moment, mesh that up with the changes that I've made, and restore it in such a way that the game persists. Now we take a quick look, we'll see that it's a bit buggy. So if we, well, wait for them to shoot at me. Well, if I shoot at them, you'll see they don't die, so obviously we've got a bug there somewhere. So we'll quickly reset it, and we'll go and track down the bug. So I can see that the collision doesn't seem to be registering. So the first thing I'd probably go and check is the physics system. So you can see the code here. As we scroll down, we found a collision there. And it does seem to actually be dealing with it, and it's triggering that collision. So how can we tell for sure? Well, because we can modify the system at runtime, we can just turn the renderer off and tell the physics system to come back on and show us what it's doing. And you can see as we fire, these hits are actually being registered, so the physics system is doing its job. So the bug must be somewhere else. So let's go down to, next thing will be the health system. So the collisions have been registered, so maybe it's the fact that, there it is. I commented that out earlier. So uncomment it, hit update, then right away you see that we disappear, and that's us dead. We can reset the game, reinstate the renderer, turn off the physics renderer, and it's hopefully back to normal. Yeah, there you go. And you can do other things in Thank you. You can do other things in environments like this. You've got the facility to take snapshots at any time. So do a few moves and click restore quickly, and it jumps back. And it's easy to see how this could be extended to a point where you could record a bit of input and you could loop it, and then you could tweak the behavior, maybe an AI agent in real time. You could tweak the behavior of enemies. You could tweak the kind of scoring algorithms, and then just keep iterating until you get it right. So that's that. So how might we implement stuff like this? Oops. So we're taught this: eval is evil, don't use it. Bullshit. It's the best thing out there when you're doing live coding. Right? Eval is your fundamental tool for live coding. And there are a bunch of things. The great thing about JavaScript, I'll say, is that it's possible to do a lot of cool-looking things without having to peek under the hood. If you want to, you can do hot code reloading, for instance, in a language like Java, but it requires lower-level machinery to do that. Whereas JavaScript allows you to do it actually within the realms of JavaScript itself. Obviously, there's some things you can't do, but there's a hell of a lot you can do. And these are a bunch of techniques that you can use. So I'll fly through these briefly. Private state, so we want to prevent the pollution of a global namespace. So this is a simple bit of code that we're tweaking, and we just want to make something move based on its velocity over time. So the setup function runs once, and the loop function runs repeatedly, just like processing, if anyone's familiar with that. Problem with that example is that we're putting stuff in the global scope, and that's bad. So the solution's quite simple. And remember, this is user code here. So this comes into our program as a string. We have to somehow turn this into code. We have to get two functions out of this. So what we can do there, we can wrap it in an anonymous function, tell it to use, obviously using strict, so there's no risk of variables seeping out of there. We can evaluate that. And we can evaluate that safe in the knowledge that we're not going to pollute the global scope. However, there's a problem. Somehow we need to be able to call these functions set up and loop in order for the machinery that's driving our game to make our simulation or whatever, to make something happen. So the solution for that is kind of straightforward as well. We inject a return at the end of this anonymous function that gives us back references to the things we're interested in. So we can carry on calling setup and loop as much as we like without any knowledge of what's going on within the closure. Next thing we want to do is provide objects to user code. So quick other example here. This is a wee example we've been using to teach kids about the basics of programming. Simple thing. You press the button, the light goes red and the car stops. And you can mess about with the code on the left-hand side to change the behavior. So, nipping back. So obviously we had to provide that car and those traffic lights to the program. It has to know to draw them. And we want to stay away from the idea of loading these things in code. Like saying load image tree.png, load image light.png, because we're trying to create something that's easy to use, something that's easy to experiment with. We'd rather be using drag and drop. We want to be, click an icon, load an image from your file system, and it appears in like maybe a props area inside your environment. But somehow we need to get these, we need to make these available to user code so they can draw them. So, again, the solution to this one's quite straightforward. We've got here a loop function that wants to draw a car. Where does it draw the car? Where does it get the car from? What we do is we know what objects are available ahead of time. So we just generate our function our method signature before we evaluate the user code, and then we pass in the relevant objects, and those will then be available within that scope. This one's a bit trickier. Global kind of. When I say globals, I don't mean like maybe globals attached to the window object. I mean variables that are global relative to the code that the user's created. So things that all their functions might be relying on. Now, when you hot load code back into the system, you want to persist these values between code reloads. You don't want the car to jump back to the bottom every time. You want to know, you want everything as much as possible. Obviously, there are some changes that you make that do naturally and necessarily make you have to restart the engine. But most of the time, you want to preserve as much of this as possible. So here we go. Here's another example. So we've got a car's got an X and Y position and a speed. And within the loop, we're just moving the car up the screen or down the screen. And if we were to change that code, maybe to draw some extra scenery, we would want the car to remain in the same position and at the same speed. So those are effectively global variables there: car X, car Y, speed. And the solution to this is that we need to be a bit cleverer than we were before, because we need to somehow identify which variables are global. So what you can do is you can use a tool like Esprima or regular expressions in blind faith, and extract the names of all the global variables, and then synthesize functions at the bottom, again, that run at the end of your evaluation. Two functions, one that returns the current values of all the variables, the global variables, and one that sets them back. So whenever you install code, you take the variables out, you evaluate the new code, then you push them back in. Now, internal eval, so if we flip back to the wee car example, I think it's gone. No, not that one. So, if we start this off, you can see here we've got a wee console down in the bottom right. And at any point, we can say, what's the current state? Where's the car? And it will tell us. But obviously, these variables here they're inside a closure. We can't get at them. So we need a way to make something like that possible. And the trick we can use here, this is just demonstrating, if you type this stuff in the console, it's going to say, no, you can't have it. So the trick here is to actually put an evaluation function inside the closure and return a reference to that function that calls eval. And then we can then call that, and then it will execute eval inside that scope. And that allows us to get at everything that's hidden in there. Blueprints. So we're moving into bigger systems now. The last few examples have been general purpose techniques that apply mainly to smaller projects. And blueprints apply when you've got a kind of prototype object that you might want to augment with extra functionality. So, for example, in the game engine I demonstrated earlier, we would create the kind of prototype object, copy some stuff across from the from the old version, create the new version from the user code, and then run the user code with the blueprint so it can augment that. It's kind of similar to the variable injection example, but it's a pattern that emerges in a more structured environment. The final technique that's useful is something like snapshots. And this is when you take a full snapshot of an individual system, and then you reevaluate your user code, and then you pass the snapshot back in to tell this object to repopulate itself based on the way it was before. So it's very simple. You give your system a method to return a snapshot and one to apply it. And then in the update routine, we just take that snapshot and put it back in. And then we throw an exception if what we've done is incompatible with the old version, in which case it'll probably be necessary to restart the app. This is kind of similar to the earlier examples. The main difference is that it's who's in control. When we were dealing with global variables, when we were scanning the source for them, it was the engine that was in control. We were trying to work out what was global ourselves, whereas in this we shift the dependency over to the actual system code itself, and each user code system is responsible for telling the engine what's important. So this is probably involves more code, less magic, but probably more reliable in the long run. Oh, sorry, there's one more. Clock sources. So if we take snapshots, that's all great, but if at any point you store dates, times, wall clock times, real times, when you come back to install that, anything that relies on that notion of time will be out of step by the delay between taking the snapshot and reapplying it. So this is the way we normally take time. What we do in a live coding environment is put a simple wrapper around it, represented by a clock object. So we've got full control of what the current notion of time is, and we would pass that clock to anything within the system that was interested in time. And then we can control that. So if we're playing back a sequence of events, we are completely in charge of how the clock increments. So I've just described a bunch of ways we can do things in graphical environments, ways we can create tools in graphical environments that allow us to experiment and allow us to do kind of cool things. But the problem is, by doing something like this, we've kind of alienated ourselves from all the tools that are out there already, all these beautiful Unix tools. We've got like grep and grep. Oh, I don't know. It's said. Yeah. So, pardon? Yeah. So how can we get a bit of this back into it? So what I've done is we've taken a bit of a cue from an operating system called Plan 9. And the distinguishing thing about Plan 9 was that absolutely everything in Plan 9 is a file. I mean, it's often said that in Linux everything is a file, but there's a bunch of different exceptions. There's a lot of little exceptions. Whereas in Plan 9, files are just the way things are done. For example, it's possible for users to mount kind of user space file systems, and then you intercept the kind of calls to those files and do whatever they want with them. And we've got something like that in the Mac world and in Linux called Fuse. And Fuse allows us to kind of mount a directory in the file system. And we can intercept any sort of calls, any requests that are made against that file system. And from there, we can act on them in our own way. So if we pop back to the game engine, wherever it's gone. So we can go in here, and if we look inside this directory, we see we've got folders for entities, systems, and transport. So we can actually go in here and say, look at entities, for instance, and list the contents, and that gives us a JSON representation of what's going on in the game right at that moment. Oops. don't use Vim very often. Sorry? Yeah, so there we go. So we can see the JSON of what the game's currently doing. And if we go in again, we see that the values are updating. But there's no reason why we can't stop there, though. We can go and look in the systems themselves. And then we can actually look at the code. And we can open these in whatever editor we want. We can grep them. We can use sed to manipulate things. We can change the values of different entities. We can even go as far as, I'll reset this so as we can see what's going on. But if we go into systems, we can even do stuff like use change mode to actually activate systems within the application. And turn them off, turn them on. So what you've got there is that you can now use absolutely any tool you want to manipulate this game environment. It's no longer a walled garden. You can use anything. You could take a backup of the entire game state just by zipping it up, sending it to your colleague, and they could load in the exact same state. No need to implement load and save. So, do one last little demo. Have I got enough time? Yeah. So, boss comes to you and says, the hello world server's broken. Travesty. So, what we do is we just we start it up. I'm going to need your help here. Has anyone got a laptop? There's my IP address, port 5000. Has anyone? Is it working? Yeah. No? All right, well, we'll just do it locally then. So there we go. Hello world server seems to be working. It's working too well. And every so often it just breaks. So what can we do? Well, let's take a log of the activity. So we'll just say, boom. And then we'll hit that a few times. And you see, we've now got a log of everything that's just happened. But we'd like some stats to see how well that's actually behaving. So we can just hook up an analyzer to the output of the request module. And let's do a few more tests. And you see, we've got some stats there. So it's succeeded 20 times, and we got a 500 status 10 times. So there's obviously some sort of bug going on there. So let's take a look at the code, but we're good developers, so we're not going to edit live code on the live server. So let's just take a copy of the live server and manipulate it here. Let's look at the code. And if I didn't know any better, that is a contrived example for a talk. So let's fix the bug. And now, rather than going through the whole process of testing again, let's just hook up our log to this and just play it back. And we'll see now there's no 500s. We know we've tested that it's working now. But the client wants to see it anyway. So we'll fire up another server, start it up, route it into this dispatcher. Test port 5500. There we go, it seems to be working perfectly. So he says put it live. There's no deployment problems here. We just reroute the public server to our working clone. And that's us done. And that's live coding.